Most of what this paper is concerned with is Giorgio Fontana's. Basically, the reason I'm a co-author is that I said, Giorgio, what if, or what would happen if you had very high intense gravitational waves focused on a very, very small area? Some of the focusing that you heard, I guess, on Tuesday had to do with Clyde Wood's focusing system. So you can get it down to essentially a diffraction limited spot. There are some ways to add a great deal of intensity on such a spot. And also, there have been many papers on gravitational wave beams crossing each other to gain even a higher intensity when they come together. So he said, well, maybe there's a nuclear effect here. And I said, okay, if one of the manifestations of the gravitational wave is it can actually bring things closer together. If, for example, you had two nuclei under a very strong gravitational wave field, you would see them pulling together as the crest of the wave comes by. So then he started doing some calculations on this. And for a certain size and intensity of gravitational wave, he said, well, this is nuclear fusion. I could bring the nuclei close enough together that they would fuse. And of course, if the result of that fusion had a mass less than the components that came together, that have some energy, would have standard classical nuclear fusion. So this started him off on his process and his paper and his study. I was involved in nuclear physics back in the 50s, but we never had anything like this, so I'm really probably won't be able to answer many of your questions, but I'll try and go through Giorgio's work anyway. Okay, what he's trying to do is, as I just mentioned, is trying to bring the nuclei together. There are different ways that have been used to do this, and you confine them at the very high speed, means high temperature, and you develop the tokamak type system that is still being studied. You can get a very high density, as indicated here, high radiation pressure, and this in the laser and particle beam confinement devices trying to, again, bring the nuclei. It's a very, very strong force. Small muons has been observed in nature, it happens spontaneously and so forth, but there hasn't really been a way to take advantage of this. Giorgio feels that using high-frequency gravitational waves, causing this bring nearer together the nuclei could allow for the unity being brought together. The objective of the study is to initiate development of technology like a fusion reactor, only done in a localized point in space by the intersection of two gravitational waves. This is his thinking. He feels fusion was given by gravity. This essentially is what takes place in the sun and stars, so why not be able to localize, have that intense gravitational field, find the stars, and do it in laboratory conditions. He uses some generators, some that I have developed, some that have been developed in China by Feng, an associate of Feng Lee's, some that have been developed in Germany. We had a paper at a MIDA presentation back in 2003 in which the Germans presented the concept for gravitational wave generation. There are other concepts that might develop a very strong beam, including some nuclear energy studies. These were done about 10 or 15 years ago in connection with nuclear bomb work. Teller was a little bit interested indeed, a couple of papers have been written in this area about how to produce strong high-frequency gravitational waves. But the experimentation there, of course, was cut off not long ago. In any event, there's a lot of literature on how to produce these beams. He felt that if you could have a amplitude, a gravitational wave, I think you'll see later on, yeah, point, an amplitude of 0.995, you could reduce the distance between the nuclei by a factor of 200. He calculates this is a way in which you can essentially initiate nuclear fission at that point. This is an extremely large value of the field. This would be something just huge. This would, in fact, be what you get. You take a look at your ruler, and suddenly you would see your ruler observation is shorter. So that's an extremely high amplitude, but it's in an extremely small volume of space, essentially the volume of space occupied by the nucleus. And you have these two beams, and they can work on the area between the two. Okay, this also represents a black hole collapse, and which he says is a common event. I didn't mention that. Okay, Landau and Lifshitz, I think, I think it was on page 375, I'm not sure, at least in my conception, indicated that indeed they could, gravitational waves could change dimensions and could change the gravitational field, which is another aspect of this. In other words, the gravitational field itself could be changed at the intersection of gravitational waves. Gravitsky and Thorne worked on this effect. So if you focus the gravitational waves into a small spot, using, again, maybe Wood's technique, to reach the amplitude of this, the problem is approximately by geometric optics, would be the frequency is high enough to provide the required amplitude. And in principle, you can do this. Now, you have to realize that Clyde Wood's work is based upon an assumption that the work of Lee and Tor that said that the gravitational wave was greatly slowed down in a superconductor, and that's been challenged, although I don't think that effectively challenged. So, but that is a fundamental requirement in order for Woods' optics to work. But if you couldn't get the optics, then you could focus beams together. And using fairly small equipment, there's no particular determination. Superconductors have to be particularly large. It can be almost any size at these high frequencies, maybe a few centimeters across, in order to concentrate the gravitational waves into a very, very small volume, perhaps about the size of a nucleus or of an atom. Well, he feels that there's some nonlinearity effects, and again, all the calculations in the paper actually prove this. There are three things that appear to him to be working together to cause this fusion, expedited fusion. One is the actual length change of bringing together the masses. The second is the fact that the gravitational field actually changes, and they tend to pull the two masses together, and then some nonlinearity effects, all of which he says tends to be in favor of producing a fusion reaction. Now you can read this as easy as I can. This is about the hydrogen, essentially what I said before. This would be done at a very low temperature, as opposed to the other things. You don't need a containment vessel, you don't need this. You focus it together. There is energy produced, probably radiant energy, that you can quite utilize effectively. This is the Christodoulou effect. Burst of gravitational waves hits a couple of particles and oscillate. And this is the change in the delta H, assuming that instead of 0.1 to 0.9, you have a 0.99. It becomes, it's essentially, the term parentheses is essentially 1. And you go, the required geometric units is 5 to the minus 11, but it's huge in terms of actual energy. In this case, it's 10 to the 33 joules. And if you say this takes place in picoseconds, you're talking about 6 times 10 to the 45th watts. However, in the generators that were discussed, not basically the two generators that I developed, but some of the other generators developed, this essentially is about 100 times smaller than the 5 to the 10 to the 42nd watts computed in this nuclear generator that Fontana is developing. The amplitude of the wave is dependent upon the energy. Basically, the amplitude of a gravitational wave, high frequency or otherwise, is proportional to the square root of the energy flux, that is the watts per square meter, and it's inversely proportional to the frequency. That's the thing that makes it difficult for high frequency gravitational wave generators, because the higher the frequency, you've got that denominator, and it's going to reduce the intensity. But if you have a huge flux, gravitational wave flux, then you begin to get a large amplitude of gravitational waves, even though, or in spite of the fact that you have a high frequency in the denominator. Furthermore, the flux, watts per square meter of the gravitational wave, that in itself, in spite of looking at the amplitude itself, causes quite an effect. And that in itself is the thing that changes the gravitational field in the neighborhood of the gravitational wave. That, I think, is perhaps the more important effect. We are talking in most of the generators of having a flux, of course, over a very small area, 10 to 100 times greater than the solar constant. That is 10 to 100 times greater than the sun's illumination on a square meter of something outside the atmosphere. It's on the order of thousands, tens and hundreds of thousands of watts per square meter. So these things are possible. Then he talks about the memory effect. This is another way of looking at the change in gravitational field. There is, according to Landau and Lifshitz, this change in the gravitational field. It's a temporary one. It's sort of a memory one that you have a change, and then in a certain length of time, in this case maybe picoseconds, this change in the field disappears. He's looking here for experimental evidence, which he got by studying some of the muon work previously. He wanted to develop 2 sets of these pellets, or sets of fuel. The very high frequency, I would say here we're in the 10 to the 12 hertz, 10 to the 15 hertz. I don't know what those would be, but very, very high frequencies. Some that might be achieved with a laser system. That's what he is currently working on here in Italy. Here are some of his equations. Here's the vibration. Here it works out what the radial velocity would be, what the average kinetic energy would be. All these equations are derived by him in the paper. You could increase the mass of electron without a muon. The energy must be equal to, works this all out. This result compares favorably with the output of the generator presented in the paper that we gave last year with the laser-driven high-frequency gravitational wave generator. For a sphere, the radius of the Bohr atom, a hydrogen atom, the power flux would be this, and it comes out about 4.7 times 10 to the 51 watts per square meter. That is a lot. flux. And then he goes through and computes this, and finally comes out with the high-frequency gravitational wave energy actually impinging on a hydrogen atom as 1.47 times 10 to the 20th joules. And this lasts for about 1 picosecond. Hopefully enough for the fusion to take place. There he then talks about the tunneling times and some other space-time changes. He feels that what he's calculated is an upper limit, that the energy required in practice would be considerably less. In other words, he was combining both the fact that the space is changing, bringing the masses together, also that gravitation itself, the gravitational field is changing, bringing the masses more together. And then he says all the nonlinear effects tend to also bring the masses together. So his feeling that the calculations that are in here are really the lower limit. Now you can read this as easy as I can. He looks at the distances between the atoms, looks at the different sizes of the gravitational wave beams, and then he comes up with this as kind of a picture of what goes on. Okay, he feels his generation technique involves X-ray laser and has essentially the frequencies, X-ray frequencies. And he has pulses of high-frequency gravitational waves coming out, having a lens here, essentially Woods' lens system, and then going into a nuclear system that these are the little peanut-shaped wave patterns, and as these high-frequency gravitational waves come through here, each time they hit a nucleus, they build up, and they build up, and build up, and finally they focus out here to some kind of collector. So this is the fusion generation for the pulses, and then this would, when focused, would produce the fusion that he's looking for. Let me see. Okay, you can read this as well as I can. His feeling is that it's time to put one of these things together. He thinks that this way of producing energy using high-frequency gravitational wave produced fusion is variable. It can be done in a fairly small volume, a couple of square cubic meters. He thinks it can be done with fairly lightweight equipment. He also brought something up that isn't really quite on here, and that is that you could remotely, perhaps, accomplish this kind of fusion. At least you could do a whole lot of disruption in any kind of matter that we got the focus of these very high-intensity gravitational waves. It's kind of a disruptive thing. And that, I think basically what he says, this is another area for nuclear physics to study nuclear physics in the gravitational environment, and to study how high-frequency gravitational waves interact with nuclei. And the theory is very sparse in this area of the interaction of high-frequency gravitational waves and matter at its smallest dimension and its highest intensity. And this is what he is trying to promote there. He's at the University of Trento. In Trento, Italy. He's been involved in this area at their university for about 10 years. Okay, I'll try and answer what questions I can.
Oh, when you talk about the destructor beam, would that be for like micro and nanoscale experimental applications, or would that be macro level for like a weapons application?
Well, you'd probably start out very small. And I don't know if there is the only weapons application I can think of is that you can remotely cause two gravitational wave beams of high intensity to come together. And in that interacting volume, probably pretty small, maybe in the nano scale kind of thing, you would have lots of strange things happen. And a lot of disruptive things, and perhaps some nuclear fusion things. That's about all I can say.
Hmm.
Okay, anything else? Now, if I can get my thing here to get together.